Here are examples of the kinds of things that show up in Chapter 3 in the textbook. The first example is dot product. Dot product is an inner product. You can take what I'm going to show you for this example and check the definitions, those three parts of the definition of inner product on the first page. But here's the mechanics of a dot product. If you haven't done this before, we say that U dot V. If two vectors are in Rn, meaning that the vector is a column, we say that the dot product is like flipping the one on the right, and in Rn it doesn't matter which one we flip, but it basically then flip the one by convention on the right, and do a row times a column. This is what we've been doing for since the beginning of this semester, is a row times a column. Notice the one on the left gives us the combination of the items on the right, but also the one on the right gives us the combination of the items on the left. So the left-rightness doesn't really matter as long as it's a row by column, not a column by a row by a column. It's just pairing each corresponding thing together and adding. Notice that when you do a row times a column or a vector dot a vector, this is not a vector. This is never going to be a vector. This is size 1 by 1. This is a number, and it's because of all the pluses. These are not n different things. This is one thing that you get when you add all of the n terms, but it's one thing, one number. Notice on your handout is the complex version. If these things are all complex, then the order does matter, because remember on the first page, or look on the first page, that symmetry is actually a conjugate symmetry for complex numbers. And so if these are complex things, we would have to put bars over all of the v's. The bars go with the second argument, or the second input to the inner product. So put bars over all the v's, and you get what's on the handout, which is the complex version of this. The real version does not care about bars. The next bullet on the examples is the function inner product. Go back to the definition of inner product, and at the end of that clip I show on the whiteboard this example actually. If you take two functions and multiply them and then integrate from a to b, notice that gives you a number. When you integrate, do a definite integral, the result is not another function, and there should be no x's anymore, because you plug in the a and the b. And so take two functions, multiply them, and integrate, and that gives you a number, and that number is what we call the inner product of those two functions. So go back to that definition video and look at how all three of those properties of inner product are satisfied by this definition of functions inner product. So functions behave like vectors. Pretty cool.